that this could get rescheduled. I am here to talk about the economics and politics of offshore wind energy, which I'm sure is pretty new to many of you. So I'll give you a bit of a background. I'll teach you a little bit of economics, and I'll give you like a really high level of some politics type stuff. But really, I want you to take away that there are lots of interesting pieces here that can make their way into kind of all of our research in marine sciences. And I'll skip this since we're running short on time and Chris covered it. But so I'm going to talk a bit about just sort of like big picture, the technology around offshore wind and some of the opportunities, because it's really interesting. It's growing really fast. And so kind of knowing what you're reading about, I think is important. I'll do a really high level look at the politics, that is kind of how the energy transition, the transition from a fossil fuel based economy that we have now to a more clean energy, reduction in emissions, that kind of political transition happens. I'll talk about the economics, and in particular, this concept called the full cost of energy generation, and sort of how that fits into the policy and politics. And then I'll end on how we as researchers in marine sciences fit in to all of those concepts. So these figures are from BOEM, the Bureau of Ocean Energy Management, which is the federal agency that's in charge of leasing areas for use in offshore wind in the United States. This top figure shows the Northeast and the South Atlantic. Down here, you can see that there's a lot of action. These green areas show lease areas, and the other colors show areas that are sort of in the planning process. There's a lot of action on the eastern seaboard, a smaller amount of action on the West Coast, and I'll come back to that in a little bit. But the point is that offshore wind energy will really change our seascape. It is kind of historically been used for fishing and shipping, and that is really kind of on the cusp of this enormous change in use. And the reason that that's happening is because there's just an enormous amount of energy potential off the coast of the United States. This figure shows wind speeds on the coasts, and you can see that wind speeds offshore are much higher than wind speeds, even in areas where we think of as really windy, like Oklahoma and the Texas Panhandle, where a lot of the onshore wind energy development is happening. Wind speeds offshore are just like an order of magnitude higher. It also tends to be more consistent than land-based wind. So this figure down here shows solar energy generation in the yellow, which obviously peaks during the day. Land-based wind tends to decrease during the day, but offshore wind is more consistent. And so this is good for sort of the matching of energy production to energy use. And it also tends to be where the people are. So, you know, the large population on the East Coast, big cities on the West Coast, it just takes less infrastructure to transfer the energy from where it's produced than if you're talking about like major wind or solar farms kind of in the middle of the United States. And the story is similar in Europe. It doesn't actually show up very well here on this screen, but this is the European seas here, and then the colors are projects that are either commissioned, operational, under construction, or in the planning phases. This growth has been driven by kind of more ambitious climate policies in Europe. So they've encouraged the switch to renewable energy sources kind of sooner than has happened in the US. But it's also grown a lot since the Russian invasion of Ukraine. Many European countries are now like, we want to be independent of Russian oil, and so have gone sort of full bore into offshore wind and other renewable energy technologies that they can produce in their own countries. And similar story with wind speeds. Wind speeds are just much higher offshore than they are on land. US and Europe aren't the only places where this is occurring. This is a little bit hard to see. This is Japan and China, Korea. So this is the Asian seas. And again, same story, wind speeds are much higher offshore. China is actually leading the production of installed offshore wind capacity at the moment. And as I was saying, this represents a major shift in the use of our marine space. This figure here shows the installed offshore wind capacity through 2022, kind of in this dark color. The orange is China, which has the highest installed capacity, followed by the United Kingdom and Germany, and then kind of a bunch of other countries have a really small amount. And then in the light color here shows the amount of offshore wind capacity that's been announced through 2028. And so you can see this really like basically exponential growth. And there are a bunch of known marine ecosystem impacts. There are lots of impacts from changes in the atmosphere and ocean due to energy removal, concerns about fisheries exclusion and displacement, socioeconomic impacts. There are a lot of marine ecosystem impacts that we know a lot about. There are a lot that we don't know a lot about, a lot of uncertainties, and I will kind of come back to this at the end when I'm talking about our role. So I'll talk a little bit about that technology around offshore wind. This is a figure of turbine sizes since the 1990s. And if you have ever been to Eastern Washington, you drive through, there's the Wild Horse Wind Farm. Those, although they appear enormous when you're driving by them, right, they're using these 2 megawatt turbines that were developed around 2000. The Wild Horse Wind Farm was installed in like 2006. The turbines that they're installing offshore right now are around 12 to 15 megawatts. So this type of size, almost 1,000 feet tall, and similarly kind of in breadth. There's kind of no theoretical maximum for the size that turbines can be. Efficiency and energy production continues to increase as you increase the size. But just, you know, things around supply chain and how easy it is to like transport a 1,000-foot piece of metal is probably the limiting factor here. So, but this kind of 12 to 15 megawatt range is what people are installing offshore right now. There's also different types of ways that these structures are attached. The most common and the most frequently installed right now are these monopiles. You also can't see that very well, but it's just a single pile that's pile driven into the seabed. In slightly deeper waters, they use these, they're called jackets. They're like little structures. And then the newest type of technology is called floating offshore wind. And these have big, giant, like many hundreds of feet wide concrete structures that float and then are attached to the bottom with cables or chains or some other type of attachment device. And there are no commercial scale floating offshore wind facilities at the moment. There are some test locations in Europe, but this really opens up a huge amount of area to potential development. Essentially, you can't install fixed offshore wind in waters deeper than about 60 meters. And so when we're talking about the West Coast, essentially it's all deeper than 60 meters. Our continental shelf drops off really, really quickly. It gets deep really fast. And so there are no areas shallow enough to install fixed bottom offshore wind. So on the West Coast, what we're really talking about is this new technology, floating offshore wind. On the East Coast, they have a nice broad continental shelf. So they're working on installing the fixed bottom at the moment. So closer to home, I just wanted to give you kind of a preview of what's happening here on the West Coast so that you can understand what's happening when you read about it in the newspaper or whatever. There are 5 leases that have been awarded off of California, off of Humboldt and off of Morro Bay. You can see that the amount of the lease bids are like hundreds of millions of dollars. So companies are really betting on this technology working out. And then in Oregon, there are 2 areas that are currently, they're called wind energy areas. And so they're being scoped for eventual leasing. We're thinking like probably in the coming months, although we're not quite sure about the timeline for those. And then I just wanted to note that there are a bunch of really large challenges that are associated with actually installing offshore wind on the West Coast. So these aren't going to happen tomorrow. This is like kind of the 10-year time scale for actual development on the West Coast. Okay, so I'm going to give you like the highest level possible overview of the politics around the energy transition, sort of the fights against climate change, and how that energy transition actually happens in the political process. And we talk about the transition from a carbon-based economy to a non-carbon-based economy where we're emitting less as a decarbonization pathway. So there are lots and lots of actions that different entities need to take to get us onto this, to get us to a lower carbon emitting world. And we call that path a decarbonization pathway. And there are 2 sort of like really high level questions that include kind of how much we reduce greenhouse gas emissions, and then how do we reduce those greenhouse gas emissions. And pondering those 2 questions kind of eventually gets you to the point where you can discuss, okay, why offshore wind? Is offshore wind a good option for our decarbonization goals? And then again, kind of at the highest level, if you think about kind of how these goals are made, a bunch of countries got together at the Paris Agreement, agreed that we as a world should limit our emissions so that the temperature changes a max of 2 degrees Celsius. And then regions and nations figured out their own emissions targets based on that global goal. States and even cities or localities or even individual businesses then take those higher level goals and work out kind of what their own emissions reduction goals are, and targets and commitments, things like that. Right now in the US, it happens to be kind of states that are leading, and I can talk a little bit more about why that is. But so they decide sort of what their targets are in emissions reductions, and then they have to figure out how they're going to do that. And there are a bunch of different options, including increasing energy efficiency, clean electricity, which of course, offshore wind is one of those types of strategies. They have to choose among all of these strategies. And then they actually have to enact policies that make those strategies happen. And so how do those strategies get chosen? Well, it's lots and lots of politics and lots of modeling. And that modeling is really what I want to talk about here today. So the main type of model that goes into these political discussions are called decarbonization models. And they require a large number of really technical data-driven inputs to drive the model. So things like, what is your energy mix now? Assumptions on energy efficiency, goals for electrification, how energy demand might change in the future. And then it requires the users to identify the scenario that they're in, like their scenario or requirements that drive that model. So what's your actual goal on decarbonization? What happens to oil prices over the next 50 years? Do we have a carbon tax? So those types of things define the scenarios. And then the model then gives you the least cost methods of achieving your goals given the data inputs and constraints and all of the scenarios and stuff that you supply it with. And then the outputs of those models will be things like, again, okay, what sources is your energy then coming from? Pollution, economic impacts, things like that. And what I really want to talk about today is this one piece of the input, the costs of energy. And as you'll see in a moment, that one piece is really complicated in itself. And so, you know, when I talk about that piece, think about how complicated all of those other pieces will be, and then how that works its way into a model. And these types of models have, you know, the same advantages and disadvantages of any, you know, really large, broad scale modeling effort. They are always subject to improvement. They're always subject to, you know, saying like this assumption isn't valid. So they're kind of continually being developed and improved, and new types of models developed for specific questions. And so just to kind of firm this up in your mind, this is a sort of public-facing policy type decarbonization model called En-ROADS that's just available on the internet. You can play around with it. There's a whole bunch of data inputs that are behind it, running it, and then you play around with these scenarios saying like, okay, I want my energy supply to be fully renewable in 2100. You know, what happens to my sources of energy? What happens to my emissions? What happens to my temperature increase? So that's kind of the very high level idea. Okay, so I'm going to shift a bit to the economics. And so remember, I'm going to talk about that cost of energy piece that fits into the decarbonization model. So I'm going to talk about the costs associated with offshore wind as it relates to a kind of energy portfolio. And there's a couple of concepts that I want to introduce first. The first is called the levelized cost of energy. And the levelized cost of energy is essentially the lifetime costs of building and operating a power plant divided by the lifetime energy that it produces. So it allows the comparison of different types of technology, wind, solar, natural gas, of unequal sizes, of unequal lifespans. It allows this kind of equal comparison of different types of projects. And so just an example of some actual data. This is the levelized cost of energy by different renewable technologies. This here in purple that declines precipitously is solar photovoltaic. And so you've probably read stories about this decline in solar prices. So that's reflected here. This blue line is onshore wind. And so you can see how that has declined a lot over time. The kind of orangish line is offshore wind. And back kind of early in the 2000s, it was kind of close to onshore wind, and that's because they were only installing them in very shallow seas. So it was essentially the same as putting it on land. Since then, they've gotten much more ambitious, and so the prices or the costs have increased a lot, but you can see again this declining trajectory. Okay, so the other concept I want to introduce is called the full cost of electricity. The full cost of energy, electricity generation is one type of energy. So the full cost of energy is the sum of private costs. So what it would cost a private individual or firm to build and generate, for example, a power plant, plus the external costs associated with the energy production. The external costs are also called an externality, where an externality is the byproduct of an economic activity that affects other economic agents, so people or firms, but is not accounted for in the market price. So an example of that is pollution that is generated by a plant dumped into a stream, and it affects downstream users, right? So a downstream user either couldn't use that water because it's polluted, or they would have to take on a cost to purify that water. So that's an example of an externality. Another example here is the Elwha Dam, which was built in the 1900s to generate electricity, but it blocked salmon from going upstream for 100 years until it was taken down recently. And that means that any user of that salmon, so whether commercial fisheries or indigenous people, or just the nutrients that that salmon provided to the ecosystem, couldn't use it. And so the cost of the loss of those uses would be the external cost of the Elwha Dam. And this is a really important concept because an individual will, or a firm, an individual firm will produce at the level that it makes sense, considering only their private costs. But a society will produce where it makes sense, considering both the private costs and the external costs. And so a coal plant is another example of something that generates electricity or energy, has both private costs and external costs. And this coal plant we can think of as generating three types of external costs. The first type is global pollution. So the climate change causing emissions of carbon dioxide and methane. It doesn't matter where in the world carbon dioxide is emitted, it affects climate change the same. That's why it's called global pollution. And there's a whole field of economics that's devoted to estimating what we call the social cost of carbon. That is the estimate of the global damages per additional ton of carbon dioxide. The current estimate that is used in the US is $190 a ton. So that's the estimate of damages across the world that our additional ton of carbon produces. A coal plant also produces local pollution. And so local pollution, it does matter where you actually pollute. So it is local to the location where the coal plant exists. It may be carried by the wind or by the water, but it's not global. So that local pollution includes particulate pollution, sulfur dioxide, carbon monoxide, nitrogen oxides. All of these things, there's a whole other field of economics that's devoted to estimating the human health impacts of these local pollutants. And it turns out that there are huge health impacts, something like $900 billion a year in health costs in the US, elevated mortality rates for adults and infants. And then sort of also included in this local pollution category are environmental impacts. So things like extraction, transportation, oil spills. You can value those types of environmental impacts, and those are included in local pollution. And then finally, there's political economy costs. And these are things like using your military to invade a oil-producing nation, needing to defend your infrastructure, needing to have strategic reserves, political instability, risk, things like that. So there's a political economy cost associated with using fossil fuels that's essentially unmeasured, although it's much more kind of in the public sphere at the moment, given the kind of Russian invasion of Ukraine. Okay, so let's look at what these numbers actually look like. These are a few fossil fuel sources of energy presented in the form of the levelized cost of energy. So this is the lifetime cost divided by the lifetime energy generation so that we can compare different sources. And in the blue is the plant level or the private costs, right? In the gray is the cost, the global pollution costs, and in the orange, the local pollution costs. So as you can see, like coal is very cheap, but if we consider those other types of costs, it is very costly compared to other types of energy. And then so comparing this to some other sources, including clean energy, so solar, onshore wind, and offshore wind, we can see that even like just considering the private costs, solar and onshore wind are now very competitive with other energy sources in terms of the levelized cost of energy. But if you take into consideration those other costs, the global and local pollution costs, they are extremely competitive, right? It doesn't make sense to install coal or a natural gas plant at this point if you're considering those local and global pollution costs. Offshore wind is still quite a bit more expensive than onshore wind. But as you know, this figure is from 2016. So if you recall that kind of decline in costs over time, that is, occurring in this figure. And then the point that I kind of want to move into the next section with is that the externalities from environmental impacts, which can be kind of a type of local pollution, are likely not zero. And that's the case for offshore wind. There's all those marine ecosystem impacts, but it's also the case for all the other sources of energy generation. And we don't currently do a very good job of measuring these and valuing them and including them in this sort of framework. So going back to this modeling framework, when we're including the cost of energy in this type of decarbonization model, what we want to do is include the full cost of energy generation for all of the sources that we're considering. And that's because these models are not supposed to represent an individual, they're supposed to represent a society's choices. And so we would want to internalize those external costs in this sort of modeling framework. Okay, so how we as marine science researchers kind of fit into this framework. Well, I hinted at it. So this is a key piece of a key research area. Understanding what these externalities are, how big they are, how significant they are, and how they may affect our energy choices kind of through that modeling framework. And again, thinking about these marine ecosystem impacts, there's a lot that we know and there's a lot that we don't know. So for example, changes to the atmosphere and ocean from energy removal, it is the potential case that removing energy from the system affects things like wind-driven upwelling. And if wind-driven upwelling is affected, then potentially primary productivity and all the species that depend on rates of primary productivity. And so valuing those changes and putting it into a framework where it can be used in decarbonization modeling type analyses is really, I think, key to really understanding the true trade-offs between different types of energy sources. Okay, so I'm just kind of wrapping up here. Thinking about those non-carbon costs, we're taking an entire energy system and we're putting it into the ocean. So there's bound to be costs. There's bound to be environmental costs that include impacts on the marine species, including endangered species, on habitats, on ecosystems, changes in ocean dynamics. There are also management costs. So changes to the way that NOAA Fisheries or ICES, et cetera, do scientific surveys and provide their associated management advice. There will be social impacts, economic shifts in coastal communities, tourism, marine safety, things like that. So identifying, monitoring, and measuring these impacts, and then, of course, valuing these impacts so that they can be used in the actual framework that guides decision-making is sort of the moral of the story here. And I don't have my notes. I had something nice to say at this slide, but I don't remember what it was. And then just wrapping up, I also want you to remember that climate change is really, really bad. And this is the climate change is a really strong signal on the marine ecosystem. This is just one figure from the IPCC report out of hundreds that you can choose from. This one happens to show projected changes in total animal biomass, including fish and invertebrates in the sea. And there will be extreme changes in the ocean due to climate change. Disentangling those from the sort of more localized effects of, for example, offshore wind or other stressors is a major challenge. But this, when we understand the impacts as being related to a framework where we're making trade-offs between a whole bunch of different energy sources and a whole bunch of strategies to decarbonize, that allows the impacts to actually be like compared sort of apples to apples in our efforts to decarbonize and avoid the worst of these changes due to climate change. Okay, last slide. This is sort of offshore wind from two different perspectives. This figure here on your left is from a decarbonization model framework. So this would be like the output from a decarbonization model showing the global offshore wind energy needs to 2050 if we're going to maintain a 1.5 degree Celsius pathway. So this 2030 bar here in the middle is sort of what we're planning for now. But this big bar is what we actually need to maintain a 1.5 degree pathway. So 8.5 times more than what we're currently planning for, 2,000 gigawatts globally. So this figure over here shows that perspective sort of from the US perspective and considering kind of all of the other sources of energy generation. This is also from a decarbonization model type framework output of it. And it's the US potential energy mix considering offshore wind. And so you can see that renewables grow a whole bunch in order to decarbonize the energy sector. Offshore wind is this blue, the dark blue sort of band up there in the middle. And so you can see that while it grows a lot, it's a very tiny portion of the overall change in both like energy generation that we need and the growth in other types of renewables. So this sort of puts it in perspective. We need a huge growth in offshore wind, but we need a huge growth in all types of renewables to stay on this pathway that we think is going to avoid the most catastrophic changes from climate change. So I believe that is it. I am just across the cut. So if you're interested, definitely email me or come talk to me. And I'm happy to talk, answer any questions now.
Thank you for working through this and giving us some time. So we have great time to ask questions. Lisa, you're welcome to call on hands.
Okay.
Yeah, thanks so much. Super interesting. I learned a ton. I guess I'm curious what you think, like how do we start putting, I know the whole like field of economic valuation is part in a bajillion ways, and I'm interested in sort of your thoughts of what is the future of trying to do valuation of these externalities when there's not an obvious way to see a price.
Yeah, very good question. And there are some impacts that have more obvious ways of evaluating fisheries impacts, for example, displacement. We can kind of model and measure, although there's lots of uncertainties involved with that. But I think the first step is kind of not stopping with, okay, there'll be an impact sort of thing, and sort of trying to understand how big or small that impact is in relation to sort of everything else, right? So sort of beginning down that pathway of comparing it to other types of impacts. In a more kind of formal valuation framework, we have kind of non-market valuation type methods that can be used, for example, if you're talking about an endangered species and impacts to that endangered species can sort of be valued through various methods. There's also a White House initiative to do more work in understanding the value of natural capital in our economy. And that kind of framework, I think, can also be used here, although there's certainly some differences. You'll have to sort of think through how that fits in. But yeah, I think the first step is really just like monitoring, measuring, projecting, and then like understanding the scale of those impacts. And that scale will help a lot in sort of being able to say like, okay, it's large, or okay, it's small. Yeah, Bill.
I think there's a really thought-provoking and covered a lot of ground. The sort of adage of think globally and act locally comes to mind. I think in any of these sort of energy production scenarios, there is this, as you mentioned, this sort of local external cost. And the immediate reaction to any kind of development is seen in that local community and then the politics associated with that. So how do you bring sort of this broader argument into that arena when there are people's lives that are going to be affected that weren't affected before, and they're going to be significantly greater than others who are going to benefit in the longer term from this kind of development?
Yeah, I think that's all kind of the question of our time, if you will. Like it's the question that renewable energy development of all sorts is facing. And the sort of increased awareness of like local projects do damages to people in that locality, almost no matter what it is, right? There are local impacts. But I think, I mean, that it's honestly kind of one of the reasons I'm kind of have stepped back to this very broad scale. These decarbonization models are used kind of at all the levels. So they're used globally, they're used by a city. And you're feeding it kind of different parameters to understand what the constraints and what the goals are. But sort of having an understanding that there are energy needs, and those needs have to be met in some way. And we're making trade-offs sort of, gosh, I don't know, I'm wrapping myself into a circle trying to answer your question. It's a really hard question. I do hope that sort of showing people that this is what's happening, like people are thinking at this global scale and trying to make decisions that will make everyone's life better. Hopefully, eventually, like, you know, mitigating those impacts, whether that's through direct payments or through other types of methods, is helpful eventually, although there's some pushback against that too. Yeah, I don't know. Yeah.
It's very stimulating. I mean, I was struck by two things: the enormous uncertainty for the floating technology, and the staggering amounts of money that are being paid for the leases. So I guess there's two questions. Is it that lease price is just a trivial portion of what it would cost them to finally implement? And who the hell's putting up that kind of money?
Yeah. Yeah, so, the lease prices are, I mean, I was sort of surprised too when those California, bids came in. They're higher than any project that had happened on the East Coast, I think, at that point. But I think they are betting on sort of a first mover advantage in California. California has a statewide goal of, I think, 25 gigawatts of offshore wind by 2050. It's something at that scale. And that is going to need a whole bunch of supply chain development, a whole bunch of port development, sort of the opportunities for capturing a bunch of that market are potentially available for being one of the first movers. I think despite the uncertainty in technology, I think they just figure that somebody will figure it out in the next 10 years and they'll be able to kind of adopt it. In terms of who's paying that money, like it's lots of oil companies have offshore wind subsidiaries now, that like you can't get around that's where the money is coming from. They're either have developed a separate company or have some sort of subsidiary. I'm sure there are ones that don't have that too, but those are the ones paying hundreds of millions of dollars for leases. Yeah.
Looking at the picture that you have behind you, what do we know about fish behavior? Do they get attracted to these things? Do they avoid these things? From a fisherman's point of view, he doesn't want to risk a net getting caught with some of these substructures. What do we know about the actual impacts of structures such as these on fish behavior and fisherman behavior?
Yeah, good question. There's quite a lot of pretty current research around all of those topics. I sort of forgot to mention that there's NOAA Fisheries has a strategic kind of science plan. There's lots of organizations, marine science organizations that have kind of planned their science around understanding the impacts over sort of the next decade or so. And then in Europe, these have been around for much longer. So there's a lot of research coming out of Europe. So there's a lot that we do know about those. Fish are generally attracted to or certain species are attracted to the structures that are pile driven into the seabed. Fishermen are generally kind of scared of them because they're giant and scary, and you can get your net caught and stuff like that. But yeah, there's a whole kind of field of research that's developing around the impacts. Yeah. Yeah, go ahead.
In relation to that, thank you very much for the talk, but in relation to that, we were talking about external costs. So are there also external benefits, right? So essentially, the times out there which are effectively fish attracting MPAs.
Yeah. I think it will probably be quite location dependent in terms of the species itself that might be attracted or maybe are avoid the noise or commotion or something. And so it may take kind of more local studies as they're being installed. But yes, certainly floating platforms may act as fish aggregating devices, and so have either a benefit for the population or a benefit for the fishery that maybe can catch them more easily. But that's certainly a good point and something that needs to be considered as well. Yeah, Chris.
So BOEM controls all this. Does NOAA Fisheries have a framework where they feed certain types of scientific information to BOEM that they can use for their policy impact and project evaluation analyses, or is there already demand for certain types of science for that, or is that under development? What?
I would say, yeah, I would say both. Yeah, so BOEM is the lead agency here. NOAA has some responsibilities around, we're a cooperating agency on their environmental impact statement, sort of whatever that means. Like we're a part of the regulatory framework, although we don't have the decision-making power. So that does connect us in a way that I think it's beneficial to provide a lot of scientific information that is useful in that regulatory framework. But then BOEM has to sort of be the yes or no decision on whether to offer a permit in a particular location. But there's also BOEM is doing planning exercises. So they're saying like, okay, where should we offer areas for leases? And that takes a tremendous amount of information because they're trying to make good decisions around avoiding fisheries impacts, avoiding marine mammal habitat, for example, avoiding different types of impacts on the marine ecosystem. And so if we can provide the science and the information to help them make better decisions about where they're placing the leases, then that will put us in a better place overall for kind of minimizing the overall impacts. So that's kind of NOAA Fisheries' role. I think that's our role as marine scientists as well, as kind of providing that information.
Cool, we're at 10 after here, and we're standing between all of us and beer. So let's take a minute and thank Lisa for being with us. And